Evening all, thanks for joining us again for another one of our Thursday night webinars. We've been really kindly joined by Rory Webster today. Thank you so much, Rory, for doing this, for agreeing. We're just hassling loads of people at the moment to come and do some education. So Rory is working at Loughborough on a PhD, and you'll be able to fill in a lot more details on that, Rory, than I will. So I'll let you introduce that a little bit more detail. Power and cycling is like a really hot topic, probably more so now than ever, like power meters and stuff being a bit more accessible, and what bikes, etc., being part of everyone's home setup and stuff. So Rory's going to go through, a little bit more about practical applications and actually what are we really looking at when we're dealing with power. So Rory, I'm going to disappear and I'm going to hand over to you if you want to introduce yourself and your talk.
Okay. Yeah. Thanks, Bianca. Thanks for having me in the webinar as well. So yeah, just kind of top up on what Bianca's already said about my research, and just a quick overview of my background. My name's Rory Webster. So my kind of academic background's done Masters of Sports Engineering at Strathclyde in Glasgow, and I'm now down in Loughborough at the Sports Technology Institute, doing a PhD in power measurement in cycling, and this is in collaboration with Wattbike. I'm also working with the Loughborough Cycling Academy. So that's the kind of performance program for cycling at Loughborough University as their performance analyst and bike fitter. So just what I'm going to cover today, I'm just going to share some of my findings from my research. So we're going to talk about power and what power is in the cycling context, and then kind of take that knowledge and try and apply it in a kind of bike fit setting. And then we're going to work through a bit of a case study of using a power meter in a bike fit. So I've quite deliberately steered away from going down the kind of academic literature kind of route too much, and tried to make it kind of quite a top level overview of power data and power meters, and hopefully as actionable as it possibly can be. So yeah, now that I've kind of introduced myself, we'll crack on and get into the kind of interesting stuff. So I think most people that will be joining us will be kind of bike fitters or cyclists, or will be working with bike fitters or working with cyclists at some point. And I imagine everybody's kind of heard it at some point, like how many watts will a bike fit get me, or kind of how many more watts will this get me, or how many watts will it save me? And everybody wants to quantify everything in cycling in terms of power. So I don't know a cyclist that they wouldn't want to, they wouldn't want more power, or to be able to go quicker for less power. So this question, how many watts will a bike fit get me? It's the kind of question that I'd imagine as bike fitters you try and steer away from kind of giving too much of a definite answer, because it's quite a broad range of what you can get out of it. Where I see the kind of the answer being is not the instantaneous kind of change in power, but more the kind of long-term approach. So you give the cyclist the option to, or you give the cyclist the ability to increase their comfort on the bike, so they're more likely to spend more time on the bike, which as a result they're probably likely to increase their power output. And again, more time on the bike, so you're decreasing the likelihood of injury, limiting the amount of time off the bike, so more volume, again more power. And then from a slightly different point of view, kind of increasing the efficiency. So in this case, what I mean with efficiency is where the power inputted, the output is higher. So from an aerodynamic point of view, for the same power output, the resultant speed is X amount faster after the bike fit. And from a biomechanics point of view, using the same physiology that the person has available to them, they're able to produce more power. So yeah, just kind of following on from from there, just a bit of an overview on why, why we use power, the benefits of power, and why it's a good metric to use over other metrics that we have available to us as cyclists and bike fitters. So I've just kind of thrown this together as a quick kind of representation of to kind of really highlight the value of measuring power in cycling. So got this this guy, and he's decided that cycling is going to be the sport for him. And before he starts his training program, finds himself a mile-long stretch of road. He's not particularly fit at the moment, and he's on his nice old slow bike, and it takes him just under 2.5 minutes. Then goes away and he does his 8 weeks of really great training. Feels significantly fitter. Feels like he's flying every time he goes out. Just feels great, and decides after 8 weeks he's going to go back to the exact same bit of road. He's definitely much fitter, and he's also bought himself a new bike, but kind of somehow ends up going slower than he did at the kind of first test. So this is just a kind of prime example of why we can't rely on speed in this instance to kind of measure performance and measure development, or to quantify performance in cycling, because the number of external factors that influence the cyclist speed or the cyclist velocity there are so many of them. So we've got rolling resistance, wind resistance, and gradient of the road. All of these things contribute to cyclist velocity. So relying on velocity might not give a fair reflection, or there are a number of variables to stop it giving a fair reflection of to kind of quantify performance in cycling. So we've also got heart rate as well. Heart rate's a kind of great tool. We can use it to kind of quantify how the body responds to different stimuluses. But heart rate's response to exercise is slightly delayed. So if we're doing short duration efforts, the heart rate might spike after the effort's already finished. And so using heart rate for that kind of effort becomes a bit challenging. Heart rate will also be affected by a number of kind of other things. So your hydration when you're on the bike, how fatigued you are, kind of different aids you're taking. So whether you have a kind of really strong espresso before you head out, that will probably elevate your heart rate slightly. So all of these things influence your heart rate. So again, it's a difficult metric to rely upon. But if this cyclist we were using as our example had a power meter on his bike for test 1 and test 2, what he might have realised was that although his speed from test 1 was higher than it is in test 2, his power output was actually significantly higher, and it was over a longer period of time. So with this, kind of what I'm trying to say is that power gives us a really nice way of objectively quantifying kind of work in cycling, irrespective of all the kind of external factors that kind of influence a cyclist. So now we've just got a bit of an understanding of why power is valuable, of why we use it. Just kind of talk about different ways we can gather power data. So primarily gathering power data in cycling started off in kind of medical applications, kind of a number of years ago, where medical practitioners would use it to prescribe exercise intensity for people in rehabilitation, so that they weren't overexerting themselves or underexerting themselves. And then going on from there, the kind of value of power was realised in a performance sport side of things. So looking at the kind of cycle ergometer that we've got down there at the bottom, that was the kind of first iteration of power measurement in cycling from a performance point of view. So these were kind of typically in kind of sports labs. They were quite expensive to access. You would fork out a reasonably large sum of money, and you would go maybe once or twice a year if you were very lucky or very keen. But there's the kind of value of them was recognised. and then so the kind of progression on from there was, I think it was 1986, SRM, they released their first mobile power meter. So they realised that these indoor cycle ergometers that people were doing their testing on were providing some really interesting data. So why can't that be of use kind of out on the road? So SRM designed and developed this power meter that you could pop onto the the crank spider. So just a kind of that nice method of measuring power when out on the road, so you could quantify performance in lots of different settings. And now moving to kind of present day, we've got any number of ways to gather power data on the bike. So you've got the kind of opposing forces measurements where they kind of calculate and estimate power from that. You've got power meters based in the pedals. You've got power meters based in the crank. Kind of SRM quarks. Rotors are still doing things in the crank spider. You've got bottom brackets, rear wheel hubs, turbo trainers, just to name a few. So they're all gathering kind of cyclists' power data in a number of different places. So it's just becoming kind of more and more accessible. And it's one of those things that's gone from being back in 1986, it was really the elite and the people that were massively focused on performance, the kind of Tour de France type riders that were adopting power, but now it's very much kind of part of the cycling language. If we're quantifying anything, we talk about watts. It's in terms of a kind of cycling discussion. If you wanted to go faster, you talk about watts. Everything's quantified in power is kind of the point I'm trying to get across. So I think with the kind of reliance on power, I think it's quite important to just be fully aware of actually what the number that you see on Zwift in the top left corner, or the number you see on your Garmin or your Wahoo computer. I think it's quite important to just have a real appreciation for actually what that data is, how it's gathered and what it's representing, rather than it just being a number that exists on its own. I think that it's important to appreciate the elements that contribute to that power number. So interestingly, power meters don't measure power. So they measure other things and calculate power as from the other measurements. So taking your power meter to calculate power, what they need, the data they need to have is the torque and the angular velocity. So with angular velocity just being a kind of engineering term or a fancier term for cadence. And then we'll go a bit more into torque here as well. So this might be quite simple for others, or a new concept for some others, just depending on background. So hopefully of interest to some people. We can talk about it a bit more. So just a bit of an explanation of what torque actually is. So if we take this crank arm diagram that we've got here, so torque is a combination of force and distance. So what I mean by that is, so when we're cycling, we apply a force straight down onto this crank at a distance from the center point of the rotation. So the crank arm is going to rotate around the bottom bracket, and we'll continually apply a force onto the end of the crank arm. So what torque is the force, the resultant force around this kind of pivot point. So a nice way to kind of think about this is if you were to try and open a door, and you grab the door by the handle and you push it open, the door opens really, really easily. But then if you're to go to the hinge side of the door and you try and push the door there, you have to apply considerably more force because the distance from the kind of point of rotation is much shorter, although the torque in both instances is quite similar. So what we'll do with, just to kind of help the understanding of torque, is just kind of work through an example in a kind of cycling context. So in this case here, we're applying 10 newtons of force at the end of the crank arm that's 175 millimeters long. So newtons are just the measurement of force, and 175 millimeters is the crank length, which we've then converted into meters here. So given that torque is equal to the force that's applied, multiplied by the distance from the point in rotation, the torque is 10 newtons multiplied by 0.175 meters. So the torque in this instance is 1.75 newton meters, which is the unit for torque. So now they've got a bit of an understanding of what this torque element of power is. I think we kind of move on and look at the angular velocity side, or what's quite often termed as cadence. So angular velocity in cycling is distance over time. So with the distance being how far round the rotation or the circle it goes. So I don't know if you've done kind of really simple physics or maths, you get the kind of distance speed time plots. It's the exact same in this case, but it's just in a rotation rather than a straight line. So using this example, so you standing next to the cyclist, you've got your stopwatch ready with 1 minute, and you count how many revolutions the cyclist does in 1 minute. At the end of the minute, it just happens that they've done bang on 60 revolutions. So in 1 minute, the cyclist's done 60 full revolutions. So to work out your angular velocity, you take the 60 revolutions, which in this case is the distance travelled, and you divide that by the time. So that the angular velocity is 60 revolutions per minute. So you've seen both elements of power now, so understand the torque and the angular velocity. To get power, both of these have to be multiplied together. So we've got the torque of 1.75 newton meters, got the angular velocity of 60 RPM. So we've got to convert the angular velocity into the correct unit, so 6.28 rads or radians per second, which is kind of equivalent. If to go a cycle, some people operate in miles, others operate in kilometers, but you wouldn't interchange. You wouldn't say you've ridden 100 miles and you did it in 32 kilometers an hour. The chances are you'd ride 100 miles and you say you did it in 20 miles an hour. So you kind of stick to the same notation. So the changing it to rads per second is just the notation that matches up with the Newton meters notation. So we multiply all that out. So we get power equals 1.57 Newton meters multiplied by 6.28 rads per second, which remember is the equivalent to 60 RPM. And the power output in this case is 11 watts. So a bit of work for 11 watts, but hopefully that just gives you a bit of an understanding of actually what's going on there. So now that you kind of understand that, just going a bit more kind of nitty gritty, actually what data is it that a power meter is gathering, and how is it gathering it, and what do we need to consider with this when we're kind of getting that data. So since power is the torque multiplied by the angular velocity, we know that the power meter is gathering both those data sets, or gathering all the data to allow us to calculate power. So the torque or the force data from a power meter is typically gathered at a very high rate. So what I mean by that is, so per second, the SRM power meter, for example, gathers 500 bits of data per second. Wattbike, for example, gathers 1,000 bits of data per second. So this part of the calculation, the torque part of the calculation, it's made up of, in this we use the SRM as the example. It's made up of 500 data bits for every single second. The cadence and the angular velocity data is a little bit different. The cadence and the angular velocity data is gathered in a slightly different way. So what we've got here, just another diagram of a crank, and this is kind of typical of an SRM power meter. So what we've got here, this is just all kind of blown up for kind of illustration purposes. But you've got And this would generally be a nice neat magnet that's just fitted onto the other side of the back of the crank. And then onto the bike's frame, you would fit what's called a reed switch. So a reed switch just records every time the crank goes round, it just records the time between, so the time taken for that one full rotation. So it can calculate the angular velocity for that, assuming that throughout the whole revolution, the angular velocity is constant, or the cadence is constant across that whole revolution. So with now kind of understanding kind of exactly what power data is, how the power meters are gathering it, we're just going to try and apply that in a bike fit setting, and kind of different things we need to bear in mind when we're doing a bike fit and using the data from a power meter. So in this case, we've got in your bike fit studio, you've decided to invest, and you've gone for what's commonly referred to as the gold standard SRM scientific power meter. So it's accurate to plus or minus 5%. So the claimed accuracy is plus or minus 5% from SRM. And you've popped this onto the cyclist's bike, and they jump on, and you're getting your pedaling balance of 70% from the left and 30% on the right. Just to make sure everyone's kind of familiar with what that means. And so you get kind of pedaling dynamics and pedaling scores and that kind of thing. So SRM's kind of breaking it down. You've got 70% contribution of the power from the left leg, and you've got the other 30% of the contribution of power from the right leg. Which is a 70-30% imbalance is quite significant. So what do we actually, other than panic, what do we actually do with this data? It's quite a significant imbalance. So there's probably some action that we kind of need to take based on this. So the first thing in this instance is just to think about how is that 70-30% split actually made. So have you looked at the rider? Are you watching the rider, and does it look like the rider's actually producing 70% of the total force with their left leg, or perhaps there's what you can see tell a slightly different story. So sometimes the way the data is presented isn't necessarily representative of what it's actually measuring. So this 70-30% split, although that's how it's how the data is displayed, so 70% of the power in the left and the other 30% of the power from the right, it actually might not be the case. So the reason this might not be the case is based on how that calculation is done. So using the SRM scientific power meter as the example, so 70% of the power within the revolution is created within the first 50% of the duration of that revolution, and the remaining 30% comes from the second 50% of the duration of that revolution. So I'll just explain that in a bit more depth. So earlier on, we just mentioned about this reed switch device, which you've got this magnet here. Pedal crank does a full rotation, and every time it passes the reed switch, it records an event. So these events happen every single rotation. So when this triangle meets that triangle, we get a recording of an event, and the distance in this instance would be one full revolution, and the time would be the time taken from the event before to this event. So what this device does is it gathers that data, it takes that duration, and to work out the 70-30% split, it assumes that the first 50% of the duration, so say it takes a second for that full rotation, the first half of that second, it assumes it's the left leg that's applying the power, and then the second half of the revolution, so the second half of the second, that assumes the power is all coming from the right leg. So in this instance, it's perhaps not the case that all the power is coming from, or the 70% from the left and 30% from the right. There's perhaps a case that the left leg is actually just not de-weighting enough on the upstroke. So as we're going in this kind of negative part of the pedal stroke, it might just be that the left leg is continually applying force in the downwards direction, but because of the way the SRM gathers the data, it's not able to reflect that. So the reason I use this as the example is it's not so much as it's not to say that this data is useless and we shouldn't use this data, because that is absolutely not the case. The data from the SRM devices, there's a lot of value in it. But I think what the kind of point I'm trying to make with this is to have the kind of full appreciation for what it is that's contributing to the data, and if the data and your kind of understanding and perception don't align, then perhaps taking a step back and thinking, like, is this data representative of the event that's taking place, or is it perhaps that the data is not reflecting what's actually happening, and the cyclist's happy, the bike fitter thinks everything's kind of as it should be, everything's looking good, but we've maybe got an imbalance of maybe 55 to 45%. I would perhaps suggest that it's maybe splitting hairs, and if the cyclist and the bike fitter are both happy in this instant, then kind of what's the concern? It's perhaps not the data you're being presented is perhaps not representative of what it's saying it's representative of. So I suppose what I'm trying to say is kind of how your kind of pedaling dynamics and your kind of pedal effectiveness scores can be quite interesting and quite useful tools, but they don't suit everybody and they don't suit every application. So if you as a bike fitter think that kind of disagree with some of the data and the bike rider not so sure about it either, there's perhaps a good chance that it is just the case that the way this cyclist doesn't suit the way that your pedal score is calculated, or it doesn't suit that the way that the kind of torque effectiveness is calculated. So just that kind of something to bear in mind. So you use the power data, use the data that power meters have got to offer, but just use them alongside kind of everything you know about bike fitting, because the chances are if you've kind of got that experience and the data's not always representative of the event kind of taking place. So yeah, with kind of all of that in mind, I kind of tried to kind of summarize what would be a kind of successful outcome from a bike fit point of view. This example I'm using is just like a kind of more performance orientated cyclist. So in this instance, the kind of common ground that or the kind of common goal that both the bike fitter and the cyclist have in common here is that they both want to make the cyclist go as fast as possible. So we can do that in a number of ways. So one of which we can get fitter, and the other is we can get more efficient. I'm just kind of breaking that down, and we can kind of highlight how kind of where I feel we as bike fitters kind of fit into that, and how that kind of shows in power. So if you're reducing the likelihood of injury, you're making the cyclist more comfortable on the bike. It facilitates kind of more training, better training, harder training, and they're less likely to miss sessions. So in this instance, their kind of increase in power or the development in their power output is improving at a greater rate than it would do if you hadn't otherwise fitted them. So if you start seeing that trend in kind of development and progression of power after a bike fit, say that's a kind of nice indication that that from the data that the bike fit's done a good job. From the get more efficient point of view, if you've got the cyclist, if you get them more aerodynamic, with the outcome being making the cyclist as fast as possible. If you make them more aerodynamic, for the same power output, they go faster. And if they're happy and comfortable in that position, again, that's the kind of success. So you've got the exact same power, but the output is that you have the kind of greater speed. Another kind of side of that is you've got better use of the already existing physiology. So if you've got a really kind of well-developed cyclist, but they've just got their setup all wrong, you kind of adjust everything and allows them to use kind of muscles and strength that they hadn't used already. That'll probably manifest itself in an increase in power. It might not be instantaneous, but if you see a nice kind of step change in their power outputs, again, it's kind of nice and reflective of a positive outcome. The last one is just kind of highlighting physical limitations that can be kind of addressed. So kind of different things that might allow the cyclist to become more aero, or might allow the cyclist to become more comfortable, or might allow the cyclist to use their physiology better, which again just allows them to be more efficient and will allow them to create more power. So and equally, we can kind of apply all of these kind of approaches to kind of cyclists with different goals. So I can't imagine there's many cyclists that don't want to increase their power, but it's kind of some want to be more comfortable, but as a result can spend more time on their bike, and as a result their power kind of increases. So more power is almost always a kind of positive outcome, and I think as bike fitters, it's kind of our job to try and help cyclists kind of given the best opportunity to create as much power as possible and to gradually develop as much power as they possibly can do. So if I said at the beginning, kind of keeping it quite top level, bit of an overview of what power is, kind of how the data is gathered, and try to apply it to a kind of case study application. Like I said, I've kind of steered away from the academic literature side of things, but if anyone has any questions about any of that, or anything in particular about the power meter or the power data, I'm more than happy to have a bit of a discussion and hopefully kind of share my opinions and thoughts and experiences. So yeah, thanks for listening, everybody. Welcome your questions.
Thank you so much, Rory, for that. We've got some questions that have come in over Twitter, actually, which would be really interesting. So I'm gonna hog you for a sec, if that's okay. Yeah. So here's one thing. Do all power measures measure in the same way? I.e., let's say you had Garmin pedals, I think, and then the Asiomas. Will they both interpret the data in the same way when they run that through their algorithms?
Yeah, there's kind of a few elements to that. So the chances are they'll gather data in quite different ways. So with a power meter, it's generally what they're measuring to gather the force or the torque element is what's called the strain gauge, and it measures how much a mechanical element kind of bends. So if you've got if you think about just a straight arm and you apply some force to it, it's kind of quantifying how much it bends, and it relates that to power. So the Garmin and the Asioma, as the example, may have different strain gauge arrangements. So the data they gather, the data in its rawest form, might actually be quite different. The kind of next level of that is what both devices perhaps manage the data in different ways. So the data in its rawest form is probably quite noisy. There's a lot of noise in it, and the signal can be quite hard to find. So there needs to be a lot of kind of filtering and smoothing to that data to make it usable. So both Garmin and the Asioma as the example, I imagine both their filtering and kind of data averaging and managing approaches are different. And then the kind of last element of that is it's got to get sent from the power meter to somewhere else. So it goes from the power meter. What the power meter does is it gathers all that raw data, it processes it into a nice kind of package, and that package has to be suitable to be transmitted via Bluetooth or ANT generally. So it has to be packaged up to kind of suit that format, and then it gets sent to your Garmin, your Wahoo, your Zwift setup. So there's a kind of number of elements that perhaps contribute to kind of what the data you see actually is.
It's fascinating. Like, it's a whole other world, really. Here's another one then, which kind of links on with that. So how important, like, let's say you're training, I think is the context of this. How important is it to use like the same power meter to capture your data?
I do think it's very important, but it's not always practical, which is a bit frustrating. So the likelihood is with a power meter that you maybe change it every few years, or it breaks and you need a replacement. And so in an ideal world, you would use the exact same power meter. The measurement wouldn't change at all over the 20 years that you decide to use it. The measurement would stay the exact same, but it's not really realistic. If for example, which I think is quite a common situation, you have a kind of mobile power meter. So you have one fitted to your bike, and you've also got like an indoor turbo trainer, and you're kind of looking for agreement between the two. I would almost be inclined to say that just don't worry about the agreement between the two, because they are measuring quite different things. So if you're prescribing training over a period of 12 months, I would try and stick to the exact same power meter for all of your kind of training quantification and kind of prescription. And just accept that not all power meters agree. And it's really frustrating, but if you get a new power meter, there's perhaps a chance that your data from your old power meter is not as valid as you'd like it to be. In an ideal world, you'd think like a kind of a what is a what, like power is power kind of thing, but it's not necessarily, or it's not the case. There's no kind of control on that. So a power meter that claims to be 1% accurate, and it could prove to be 1% accurate as well. If from the same company, if they make a turbo and a crank, I don't think anyone does, but a turbo and a crank, if they both claim 1% accuracy, the devices probably still won't agree. And to be honest, they probably shouldn't agree.
You know, you only have to read like the forums to see what everyone has to say about the variability in their survey trainers as well. So there is that. So Barney has asked, I can put this on the screen actually so you can see it, Rory. Barney's asked about like the Garmin claim around their 1% accuracy for their new pedals. I don't know if you're familiar with this, but he's interested in hearing your thoughts on that.
Yeah, thanks for sending that across, Barney. So I mean, it's interesting. I think what I would really love to see is how they decide it's accurate to 1%. So for it to be accurate, you're kind of assuming they're relating that back to something. So it's 1%. is 1% accurate in comparison to something that measures better than it does. Which, yes, different settings you kind of use. Different companies use kind of fancy sensors and kind of different kind of fancy, expensive pieces of hardware. And I think what's interesting is the claiming kind of accuracy to 1%. There's not much transparency in just kind of where that 1% is. Is that across the full range, or have they just tested that between maybe 0 and 900 watts, or and is it 1% accurate? Kind of with like maybe between like 200 or 300 watts, and actually out with that it's like 2 or 3%.
Yeah, that's true. Yeah.
And then it's all very dependent on what they're comparing it to as well. So there's lots of kind of factors that play to that. Personally, I think what would be more interesting is if devices first were to publish how precise the data from this singular device would be, so that you can say that your data today will be within a 1% range of what it is tomorrow, and so it's a precision point of view rather than an accuracy point of view. So with precision being how repeatable under the exact same conditions, how repeatable that measurement is.
Arguably, Rory, with that, can power pedals actually be that accurate? I.e., like versus a crank-based measurement, for example, because of the noise.
To be really straightforward, I'm not sure.
Yeah.
It depends how they gather the data, and yeah, to be honest, I'm not 100% sure how they do that. There are, if anybody does know, I would love to. I would love to discuss it with them. So there's kind of different strain gauge arrangements and different setups, and some will be more noisy than others, and some will be more repeatable than others. I think so. Something that would be repeatable would generally be a strain gauge mounted onto a very basic shape. So what a strain gauge is trying to do is work out how much something's bending, but and they're kind of using, it's not overly complex, but they're using relatively complex kind of engineering to work out how much something's bending and relating that back to the force. So if you fit a strain gauge onto quite a complex shape, so for example something that's if you're to fit it onto a sphere with a hole in the middle, to model that, kind of how that's bending is quite challenging. But if you were to fit the strain gauge onto a really simple shape, it becomes a bit more simple and a bit more repeatable. So I don't know. I don't know if a pedal power meter is going to be less good or more good, more or less good. But kind of hopefully understand the theory a wee bit.
John's asked about like the use of crank lengths for power. So he said you used a 175mm crank in your example, but what are your thoughts when using shorter cranks? For example, like 170mm cranks for riders who might think that a 175mm suits them. He said this may be going down a rabbit hole or deep rabbit hole.
Yeah, that's quite an interesting one. And I'm not sure. I'm not sure I've quite gathered my thoughts on it fully. I've read kind of different things about it, and different evidence that kind of conflicts, and some saying that you can't perceive a 5mm difference, and it makes no effect to the power output, and the force production is the exact same. And but at the same time, I'm a little dubious on some of the results just based on how the data is gathered. So I think a lot of the outcomes of studies that look at different crank lengths, the outcomes are quite good and interesting outcomes, but they've kind of they haven't quite got the tools to give them as much confidence as they should do. And it's definitely not the fault of the researchers. It's the kind of not getting the data that's potentially promised. So yeah,
a lot of variables.
In theory,
well.
In theory, if you go with a shorter crank to create the same amount of torque and same amount of power, you have to apply more force. But there are other elements in that as well. And then there's the other argument that it's just some people can't perceive that a 5 millimeter difference, for example. The reason I chose a 175 was just because it was easy maths. there wasn't too much logic to it. I think from kind of testing different crank lengths, I think if there's a kind of biomechanical reason to go with a shorter or longer crank, something that a bike fitter's identified as a help or a hindrance, then go with that and let the power take care of itself. I would say. Again, interested to discuss it, hear other people's thoughts.
Yeah, for sure. I think it is a big rabbit. I think it's multiple rabbit holes.
Yeah, there's a lot of trade-offs.
Tim has asked about capturing data indoors versus outdoors. So do you think that there can be variables between that?
With respect to data quality, or just kind of what the person's capable of outputting? Or
not sure, Rory. I think he's
okay. I'll maybe try both then. From an output point of view, generally you can produce more power outdoors. Not everybody, but the kind of general kind of understanding is that you can produce more outdoors. In terms of the data quality, I would imagine it's going to be more repeatable data indoors, given that there are less variables, kind of less movement. It's potentially a less kind of dynamic movement. So the power meters are power meters are great as engineering things, but when you introduce humans with engineering, they generally don't work too well together, because an engineer likes something to have a perfect outcome that's kind of ideal, and humans are anything but perfect. They're quite variable, and when you go outside, you become even more variable than you would be inside. Also, just see Tim's popped up in the bottom corner. So okay, So as far as I understand, and from what I've read, Tim, kind of your outdoor output generally will be higher than your indoor output. I believe it's attributed to kind of cooling, potentially kind of how you apply the power as well. I haven't looked at that stuff in a while, but yeah, the kind of general understanding is a bit more outside than inside.
Well, then, what data should you use to train indoors? That's the rabbit hole again.
Yeah, this is maybe wandering out with my wheelhouse a little bit and going a bit more physiology focused. But,
yeah.
No, I'll maybe take a step back and say I won't answer that. I'm not too sure. I don't think that's my area of expertise.
We'll probably ask Dr. Pringle that one.
Yeah, I'd be intrigued to hear the answer.
Yeah, Yeah, for sure. Robert Tong has he said, "Thank you, Rory, but can you say maybe how riders could verify that their power meters are accurate? If you know the answer."
Yeah, I'm just.
I guess it depends a little bit on the power meter as well, right?
Yeah, very much. Yeah. Yeah, I'm just trying to think how. Well, so I think fundamentally you can't verify that it's accurate at the moment, which is a really rubbish and unsatisfactory answer, I imagine. The reason you can't, or I don't think you can verify it as accurate at the moment, is because we don't know what power meters are tested against. So different people. So in literature, in kind of academic research, what's quite often done is they'll have power meter 1, and they'll compare it to power meter 2, and power meter 2 is the new power meter on the block, and power meter 1 is the one that's been around for ages, and the quality of that measure is the quality of the new power meter is compared against the old power meter, but that old power meter's not potentially not been validated either. So it creates a bit of a kind of hierarchy, where there's lots of work at the bottom where you've got all these new novel power meters that are being compared to the level above. But when you look at this level above, there's maybe another level above that, but beyond that, it's perhaps not as well done. To be really straightforward, I'm not sure you can verify that your power meter's accurate. I think what you can do is verify or check the agreement between different devices if that's of interest to you. So if you've got if you have one power meter and you're getting a new power meter, what you perhaps want to do, so we'll compare. We'll say you've currently got a crank-based power meter, you've got a turbo as well, and you're going to buy yourself a new crank-based power meter because the one you've got doesn't have the features you're looking for example. So what you can do is test your current power meter against your turbo, which is kind of the control in this instance. What you need to be really careful of doing is controlling everything you possibly can. So when you start changing gears during that test, you're introducing another variable, and it's because the power is measured at the rear hub on the turbo, and it's measured at the crank on your mobile power meter. If you start changing gears, you're introducing kind of efficiencies. So it's not that range that the turbo power meter comes in gets broader and broader because there's more elements to that measurement. So if you control what gear you're in and you control as much as you possibly can, it'll give you a kind of best comparison. It's not perfect, but from a kind of user's point of view, from a user's point of view, it's probably the best approach.
I'm aware that we've taken up a lot of your time, Rory, so we've got 2 questions left, if that's okay. Well, there's a few more than that, but I think we'll stick to 2. So
yeah, no worries.
John, I don't know if you know John, but he has wondered if you'd used Infocrank for bike fitting.
No, I haven't used an Infocrank. I do like what Infocrank do and talk about and present though. I like that. I like that Infocrank have been a bit more transparent than the majority of companies in terms of kind of I think they get a lot of the sensors they use on their cranks verified by a third party, which I think is again, it's not perfect, but it's a really nice kind of first step to standardizing things in power measurement. What's the second part of the question? Correlated motion analysis data with high-speed torque analysis. Yeah, so most I hope I'm understanding your question right. With the motion analysis side of things, have gathered quite a bit of data on that, just to look at kind of how a cyclist's pedal stroke looks within a revolution. So if we're thinking about kind of the whole way around the circle, the pedal stroke isn't a constant speed around the whole circle. There's a bit of fluctuation in it, so you kind of get like this kind of wave profile, and looked at a similar thing in under sprint conditions. So starting from 0 RPM and ramping up as quickly as possible, and looked at how that profile looks. So taking kind of commercially available power meters and compared that with kind of motion analysis systems. So the Vicon motion capture system, which is similar to what bike fitters use. It's just cameras. It gathers high speed motion analysis data. So gather that data, which kind of looks quite interesting. I'm kind of going to continue to look at that. And with the high speed torque analysis, I think most power meters gather quite a high sampling rate of torque. I think that's what you mean. If I misunderstood it, then ping me a message. I'm really be interested to chat about it. But so I think from my understanding, I think most of the time the torque data is going to be of reasonable quality, or reasonably reflective of the event that's taking place. With the cadence data, perhaps not. And I suppose that the two kind of coupled them.
The last question, Rory, that I wanted to finish on, it's a hot topic at the moment, is what are your thoughts on the Shimano SPD power meter that's coming out, or is out? I don't know if it's out yet.
Yeah, it's certainly on its way, isn't it? I mean, I don't know.
Intrigued.
I think I'm trying to be quite. Yeah, I think it's really, really nice that you can finally, or hopefully or that power meter companies are realizing that people want power meter pedals, but also want a good quality pedal, rather than a kind of 800 quid set of pedals that function like a 30 quid set of pedals, just in terms of like the actual pedaling feel. So I think from that point of view, it's quite nice, and hopefully, ignoring the power side of things, hopefully it's actually a nice feeling pedal. From a data point of view, I'd be wrong, and I don't know to say yet. The old vectors, they've changed it to the Rally now, I think, haven't they? Rebranded it. But the old vectors, the way they gathered data should have, in theory, been quite nice, but somehow a lot of customers didn't seem to like the data. So there's perhaps something going on in there with the kind of data management. I think inherently a power meter pedal, you get a bit of noise from it, and it will be more noisy than power data from somewhere else. But I think it's got potential, and it's quite nice that they're fitting it to a nice pedal body now. Be really intrigued to see kind of what the data looks like. But no, I'm not sure yet, not having not used them or seen them.
People will still use them on the road as well, like I know it's exclusive for mountain biking, but it would be interesting to see what the uptake's like on them, for sure.
Actually, I hadn't even thought kind of so narrow-minded, just thinking road biking there, but the mountain biking, I think that the mountain biking side of things will be, I think it'll be really interesting.
Yeah, really interesting.
I'm really not convinced that current power meters quite are appropriate for mountain bike type riding. So I'm intrigued to see what Garmin do. I think because of how dynamic and variable mountain biking is, I think there might be a bit of chaos in the data. Just something as simple as approaching a corner, and rather than doing a full revolution, you do kind of half a revolution and back. Just how that's reflected in the data, kind of how they couple that with how they couple that kind of movement data with the torque data, and then just kind of really practical things like what happens when you whack it off the ground, which in mountain biking is common. Like you whack a pedal, and I think I'd be quite upset if I whacked a 500 quid device off the ground, and I think I'd be more upset if it broke it, and even more upset if the data from it was useless. So I don't know. I would love them to be. I would love them to be great, and I'm really intrigued by it, but maybe a tad skeptical. But like I say, I really hope they work, because if they do work, it's really nice.
Time will tell, huh?
Yeah, for sure. Yeah.
Cool. Right. There are other questions, Rory, but what I'll probably do is just put them to you, like maybe on Twitter and stuff, and then that way, because thank you so much for chatting through that. It's been really, really good. Like, I've learned lots, and I hope like everyone else has that's watching either now or after the fact. So yeah, let Rory know how you get on with it, and if you've got any questions and stuff. All right. But otherwise, that's us done now. So yeah, over and out, guys.
Thank you.